So the last part of the applications of equilibrium is solubility equilibria, which deals with the equilibrium involved in the dissolution of an ionic compound, aka a salt. So what does it mean? KSP is the K equilibrium, and SP is solubility product, which refers to the product of the concentration of its ion. So if you have, for example, a solid, I'm going to call this a generic solid, AB solid, and it dissolves in water, and it's going to break up into the A positive ion and the B negative ion. So think about what is happening, again, at the molecular level. You have AB solid, and it goes in here. I'm going to call this AB solid. It's going to break up to form A positive and B negative ion. And if the solution is saturated, that means it's reached the point of maximum solubility, and you can't dissolve it anymore, you're going to have AB solid down here at the bottom that is yet to be dissolved. So what is happening is that you have dissolution that's occurring in the forward reaction, and that would be referring to this one, and we call this precipitation or crystallization, and that's the reverse reaction. And so what KSP does, the value of KSP denotes the concentration of the product, or rather the product of the concentration of the ion, aqueous ion, once the maximum solubility point has been reached. And if the concentration gets any higher, then some of that will precipitate, and the reverse reaction will predominate, reverse process, in this case being this product precipitating to form AB solid. Okay. Now, because of the equilibrium expression only includes aqueous and gases, the expressions for KSP in this case will be A positive and B negative. You don't put it over AB on the bottom because that's a solid, and solids don't have any concentration. Okay, so let's put into some calculation for KSP. Okay, so picture this. You have a solution of copper 1 bromide, so that would be CuBr solid, and it undergoes dissolution when you put it in water to become the Cu positive ion and the bromide ion. Okay. So KSP would be Cu positive and Br negative. And given the solubility of this in grams per liter, like if you have 1 liter of water, what's the maximum amount of grams that can be dissolved? In this case, it would be 2.9 times 10 to the negative second gram. Okay, so let's do this. We're going to assume that we have 1 liter. So we have 2.9 times 10 to the negative 2 grams of CuBr. And you're going to divide that by the molar mass, okay, to convert that to mole. Okay, and in this case, this would be 143.45 grams per mole. And then that approximates to 2.02 times 10 to the negative 4 mole. So therefore, if you have 1 liter, we can say that the concentration, okay, dividing by that would just be 2.02 times 10 to the negative 4 molarity. Okay, now, I think it is a good idea to understand what's happening here. Make sure you pay attention to the molar ratios at this point. So for every 1 mole of CuBr, you're going to get 1 mole of Cu positive ion and 1 mole of Br minus ion. So because of that 1-to-1 ratio, we can assume that the Cu positive and the Br minus concentrations are equal, and that will come out to 2.02 times 10 to the negative 4. So that Ksp value would be 2.02 times 10 to the negative 4. And I can just go ahead and square that because that is the same for both Cu positive and Br negative. Okay, and so that comes out to roughly about 4.08 times 10 to the negative 8. And I want you to notice that that Ksp value is very, very small, is significantly less than 1. So that means that a reactant will be highly favored, and you're going to have a very tiny, tiny, tiny amount of product. And that should come as no surprise, really, when it comes to Ksp, because we're dealing with salts that are very slightly soluble, they're mostly insoluble. So in the case of this one, when you dissolve this in water, it's not going to dissolve very well, and you're going to have mostly CuBr solid with a teeny tiny bit of Cu plus and Br minus ion. Okay, so let's go ahead now and go backward. Let's say we have the molar solubility, and actually not really need to go backwards, but there's a little bit of a change in how you calculate what Ksp is in this case. So go ahead and take a moment to pause the video, write the dissolution equation, and also write your Ksp expression. Okay, so if you did this correctly, this is the equilibrium equation that you would have gotten, as well as the expression. The charge of bismuth is 3 plus and sulfide is 2 minus, and you need to make sure that you balance the equation correctly in the end so that you have the correct Ksp expression. And once more, we don't include solid. Okay, so the molar solubility of this is 1 times 10 to the negative 15th, and we're talking specifically about the Bi2S3. Okay, and that's the molarity of this. Now, because of the 1 to 2 ratio, 1 to 3 ratio, you're going to multiply this number by 2 to find the concentration of the bismuth ion at equilibrium. So that's going to end up being 2 times 10 to the negative 15th. And then this one will be 3 times 10 to the negative 15th. And these are the equilibrium values. So we can say Ksp equals 2 times 10 to the negative 15th squared 3 times 10 to the negative 15th cubed. And it's going to come out to a very, very, very tiny value, which indicates that this compound is very, very, very insoluble. Okay, so when I put that in the calculator, I end up getting 1.08 times 10 to the negative 73rd. And once again, that number is very, very, very small, so there's barely any dissolution that involves Bi2S3. Now, this time, this is the one I meant where we're going backwards, where you're given the Ksp value, and you need to figure out what the molar solubility is, the solubility of the salt itself. So what I'd like you to do is go ahead and once again write the dissolution equation and the Ksp expression. And there's my work for it. So you don't strictly have to do this, but I highly recommend you do this for purposes of helping you understand what's happening. We need to find out first what the concentration of each ion is at equilibrium, or possibly. So let's go ahead and start off with this. We need to make an ice table. And we're going to ignore the CuIO32 here. And before any dissolution has occurred, the concentrations of these are both 0. And this is going to increase by a factor of x, and this one would increase by a factor of 2x with the 1 to 2 ratio. So we have x and 2x. So Ksp is 1.4 times 10 to the negative 7th, and Cu2 plus is x, and IO3 negative is 2x squared. So pause the video and take a moment to use your skills math skills to determine the value of x. So if we did this correctly, you would have gotten a value of 0.0032 molar, meaning that the concentration of Cu2 plus was 0.0032 molar, and this would have been 0.0064 molar. So given the 1-to-1 ratio between the CuIO32 and the Cu2 plus, this means that the molar solubility of this must have been 0.0032. You could say molarity, but I prefer to say moles per liter because we're measuring how many moles can be dissolved in 1 liter, specifically when it comes to molar solubility. We can say that a molar solubility is the same thing as X when solving under the ice table here. Okay, so let's look at this next one and see if you can work out how you can do this problem just by looking at KSP value versus when you actually have to do some of the math work. So go ahead and pause the video and look over these questions. Okay, so when it comes to determining the greatest solubility from KSP value, it's very important that you look at the stoichiometry of the coefficients. So for the first compound, you can see that it separates into X positive and Y negative. And the second one is ZY, I'll put the equilibrium by the way, Z positive and Y negative. So because in the first one, the stoichiometry of the ions is 1-to-1, you're going to both be, it'll end up being KSP equals X squared in both cases. So therefore, you go with the one that has a higher KSP value because the higher KSP value means that more product would be, or products are generally more favorable relative to the other one. So in the case of this one, ZY has a higher KSP value, as evidenced by its, so therefore have a greater solubility as a result. And its higher KSP value means that more product will be present here, so you have more of these ions compared to this one over here. Okay. Now for the other one, you can't quite do the same thing because in the first one, it is X2, Y3. Equilibrium is going to be 2 X3 positive plus 2, 3 Y2 negative. And you have a 2, 3, whereas the other one is a 1-to-1. So you have to do the math behind this one for both of them and solve for X in both cases to determine whichever one has a greater solubility. So that's a fair word of warning. If you can compare KSP values directly as long as the stoichiometry of the coefficients are the same. But if they're different, that's when you have to do the calculations like we did in slide number 3. Okay, so the next thing we're going to talk about are the factors that affect solubility. And you need to make sure that you refer back to what you've learned beforehand with acids and bases because that comes up pretty prominently in this section. Okay, there's 4 factors that impact solubility. And we're going to focus mostly on the first 3. And for the complexing agent, we're not going to worry too much about it, although you're going to want to know the impact of hydroxide because that ties in directly to the solution pH. So first thing, with temperature, you should understand that an increased temperature, okay, of the surrounding, okay, usually the water, you would have a greater solubility of a solid. Think about how steam cleaners work for carpet. If you have a higher temperature of the water, that allows the steam cleaner to dissolve some more of the dirt that's stuck in the carpet. So more of it will dissolve in the water, and then the steam cleaner will then suck up that water. So a higher temperature will lead to a greater solubility for solids specifically. It does not apply to gases. Okay, next thing to talk about is the word common ion. And just like Coulombic attraction and polarizability, this needs to be part of your lexicon. Okay, you must know the word common ion effect. Okay, so the main key point of the common ion effect is that solubility decreases when a common ion is added. Okay, that said, I don't want you just to memorize that. Okay, so let's see if we can look at some of the examples of how the common ion effect might work. Okay, let's consider this is silver chromate ion, and it's being dissolved in water to become silver and chromium. Okay, if you add more chromium, okay, that would be, chromate. If you add some more of the chromate ion, this part would increase. What happens to the equilibrium? It will shift to reactant. And more specifically, Ag2CrO4 solid will form. Okay, so when more solid is forming, I would like to indicate that that is precipitation, not dissolving. Okay, and when precipitation is happening, okay, that means that solubility decreases as a result. Okay, so we call this the common ion because this is, if you look at this, we have the chromate here and the chromate ion. And that chromate ion can be added in the form of another salt. And how could you add it in? It could be something like K2CrO4 or MgCrO4. We put a soluble salt and we put it into the water, and if that salt dissolves, it'll provide a source of that common ion. Okay, right here. Okay. So let's consider this one. In which of the following aqueous solutions would you expect Ag2S to have the lowest solubility and the highest solubility? So Ag2S, solid, okay, become 2Ag positive and S2 minus. So if you look at pure water, okay, this is H2O, and remember the KSP expression, Ag positive squared, S2 minus. By adding water, think about what that does to concentration. Okay, so concentration will decrease. So if the value of this decreases, and the value of this decreases, this means that Q, okay, will have to be less than K. And if Q is less than K, shift to product, so more will dissolve. And that shouldn't be surprising to you when you add more water, as long as some solid is present, then the solid will dissolve and solubility will increase. So Q is less than K, shift to the products, solubility increases as a result. Okay, the second one, okay, let's see what's happening. You have 0.01 molar of Na2S. So because you only have one S2 minus ion for every one Na2S, that means the concentration of S2 minus would equal 0.01 molar. In the second one, the concentration of S2 minus would equal 0.03 molar because of that 3 subscript. So comparing these two, look at which one has a greater concentration. And it's going to be the second one, the greater concentration of F2 minus. So by the common ion effect, the addition of these two, both Na2S and Al2S3, will shift the equilibrium to the reactant and decrease solubility. So I would note that both decrease solubility, okay, Q would end up being greater than K because you're adding more products. So Q is greater than K. Okay, but Al2S3 has a higher concentration of the common ion. And therefore, the Ag2F will have lowest solubility in Al2S3. So make sure you make use of that common ion effect terminology. I could very well use it on an upcoming free response assessment, just so you know. Okay, folks, let's bring in your favorite acids and bases. Weak conjugate acids, weak conjugate bases, strong acids, strong bases, that's going to come in play. You can apply the Chatelier's principle to talk about how changing the pH will affect the solubility of a solid. So let's think about this one. Let's look at this example. If PO43 minus is removed, okay, we would increase solubility. Okay, because removing this will cause the equilibrium to shift to the product. So how can PO43 minus be removed? Well, this is a weak base. How do we know it's not negligible? Because this conjugate acid, HPO42 minus, HPO42 minus, is weak as well. So how can we remove it? We can add, H3O plus H plus ion, typically from a strong acid like HCl or HNO3. And remember that because it's a weak base, it's going to want to gain those hydrogen ions, maybe to some extent, and therefore, when PO43 minus being removed by H plus ion, that's going to cause the equilibrium to shift to the right to the product. So remember that by adding H plus ion, you are decreasing the pH. Okay, so by decreasing the pH, by adding H plus ion, you're removing PO43 minus ion. Okay, but remember that the base here has to be weak. It can't be negligible, because if it's negligible, then it will have no effect on whether you remove it or not on the solubility. Okay, in terms of changing the pH. Okay, so what to note is that when either ion is moderately acidic or basic, the solubility can be changed by adding a strong acid or a strong base. Okay, so let's take a look at this one. Let's write the dissolution of CuOH2. Okay, and we're going to make this Cu2 plus aqueous plus 2OH minus aqueous. Okay, so if let's say we increase the pH. Okay, and how do we increase the pH? Well, that's like adding a strong base such as sodium hydroxide or potassium hydroxide. Okay, that would be increasing the OH minus concentration. And that would cause the equilibrium to shift left to the reactant. and that means that solubility would decrease since more solid is forming. Okay, now lowering the pH by adding an acid, well, acid reacts with the base here, so by lowering the pH, that means that the OH minus is going to decrease. And when you decrease the OH minus, that's going to cause the equilibrium to shift right to the product, and solubility will increase. You have to really think it through because it's very easy to make careless mistakes in this process. And I should also add that in this first example, this first part right here with increasing the OH, this is also another example of the common ion effect. Okay, so by increasing the pH, by increasing hydroxide, there's an example of the common ion effect, which shows that in the presence of a common ion, the solubility will decrease as a result. Okay, so let's look at the next one for HgCl2. So we write the dissolution equation and 2Cl minus. Okay. So decreasing the pH, remember, means adding acid, aka H plus and H3O positive ion. But you remember that Cl minus is a negligible base because its conjugate acid is HCl, which is strong. So adding any kind of a strong acid will have no impact on this solubility because that Cl minus is negligible. So no effect on solubility as a result. Okay, let's go and do this with one more example. So I'm going to pause the video and think about this. So applying the thinking, adding an acid, again, means adding H plus ion, which would decrease the pH of the solution. So H plus, H3O plus ions are going to react with the base, which in this case is the carbonate ion. And the carbonate ion is a weak base, so it will therefore react with the H plus. Okay, so the addition of the acid would mean that the carbonate ion concentration would decrease. Okay, and then the equilibrium will shift to product, and the products are aqueous. Okay, and therefore solubility will increase as a result. Okay, this last one here, I'm not entirely sure if the AP exam covers it, but I don't think it's entirely outside the realm of what they expect you to know and what to not know. When you did the Making a Rainbow lab, we talked about complex ions briefly, and again, you don't have to know how they are made. You need to know about the terminology of complex ions. You just need to recognize that a complex ion can be formed. Okay, so what this equation is saying here is that ammonia molecules can react with silver ion to form this complex ion right here. So when you see Ag positive as part of an equilibrium, the NH3 can react with it to cause it to decrease. So when we're specifically talking about AgCl, we're referring to AgCl solid breaking up to form Ag aqueous and Cl minus ion. Okay, so what this equilibrium demonstrates right here, once again, or not, this equilibrium demonstrates is that adding NH3 means that it will react with the Ag positive. So in the case of this one, we would say that adding NH3 to this solubility equilibrium will cause Ag positive to decrease. Okay, equilibrium will shift to product. And once more, solubility will increase it. Okay, I think that's enough about the KSP business. So if compared to the acid-based stuff, titrations, it's not nearly as bad, but it can get a little tricky, especially with this whole decreasing the pH bit and all that. All right, that's it.